Okay, hello physicists. Welcome to our first class period of our third unit. This is where we are in the semester. We have already done a boring first unit where we just defined how to talk about motion. Then we did a little bit of an interesting second unit where we talked about how to add forces together and get objects to accelerate. And now we're going to really start cooking because we've got all of our definitions in place. We've got sort of a framework for talking about motion. And I feel like this is sort of like, we're physics toddlers at this point because we've sort of learned the language and now we're finally getting enough skills to really cause some trouble. So what we're going to be working on in Unit 3, basically, we're going to be going from the idea that you can describe an object just as a point to describing groups of objects and objects that can spin and roll and all of that sort of thing. Okay, so instead of just having these very simple objects, we're going to describe more realistic types of objects and groups of objects. So in this chapter 9, we're going to describe systems where you can have collisions and explosions and how to get a handle on this so you don't just have to do the math for every single one of those particles individually. And so that's what we're going to be talking about today. In chapter 10 and 11, we're going to be talking about, things that roll, things that spin. If you want to think about it sort of heuristically, the problem with those sorts of physical systems is that, we were talking about kinetic energy, for instance. But if you have a big disk of stuff, the objects on the outside of the disk are going more, they're moving faster than the objects on the inside of the disk. So they have greater kinetic energy. So, as a result of that, if a disk is spread out far, it's going to be harder to get it to start spinning than if it's all concentrated in the middle. So we're gonna work on that quite a bit, and then we're going to kind of put it all together in chapter 13 by talking about gravitation, and that I think is my favorite subject in Physics 1 because it's the first sort of actual physical law. F equals ma. That's a framework for talking about physics, but gravity, that's something you can go in the lab. And you can measure gravitational forces directly. And it's something interesting, surprising, and, kind of true. Okay, so today is going to be kind of a tough video. Not because any of the individual ideas are hard, just because we're going to be introducing a lot of new vocabulary. And so I'm going to just say the vocabulary now, and the reason I'm saying it is to, create a space in your brain for it. It's not that I expect you to get everything off of this slide. It's just sort of a preview, and so we're going fast through it, then we're going to go slowly. So here's what we're going to be looking at today. First, we're going to be talking about the idea of a center of mass. So the idea is that if you have several different particles, you want to describe them by a single point, and that point is going to be closer to the places where you have lots of mass rather than a little mass. So it's basically a weighted average of where all the mass in your system is. And the reason that's useful is that you can then go from all of those points in your object, or all of those different particles that you could define as your system, and describe then your system essentially as a particle. Okay, so that's a little confusing, but hopefully we can make some sense out of it. Next, we're going to, just the same way that we re-described problems that we had already done in terms of energy, we're also going to re-describe our problems that we know how to do in terms of momentum. So, for instance, you remember that we had a quantity called the kinetic energy, 1/2 mv². And this told us something about the motion of our particle and the bigger the mass it had, the more energy that that object was said to have for the same speed. However, it will also turn out to be useful to us to have a form of this kinetic energy idea that has direction. And so we introduce something that's sort of like it, but instead of just being a number that doesn't have any direction, we want to have something that does have a direction. So we introduce the idea of momentum. And just like we had the idea that you could have a kinetic energy at the end of a process and a kinetic energy at the beginning of a process, and the way that you would go from your initial kinetic energy to your final kinetic energy was by adding work. We're going to do something like that with momentum. Momentum is the mass of an object times its velocity. So this can be positive or negative. It has a direction. What we're going to do is have our final momentum equals my initial momentum plus the impulse. Okay, so you can see that it looks a lot like this, where we had final kinetic energy equals initial kinetic energy plus the work. Work was force times distance. This is going to be force times time. Okay, so the average force times the amount of time changes your momentum. So the initial momentum is changed into a final momentum by applying an impulse. That's applying a force for some amount of time. Okay, so again, it's not always easy to see when you start something like, okay, we already knew how to do this startup problem. Why are we continuing to add on more and more layers of nonsense on top of it? But trust me, this is one that really does yield some dividends. And I don't know that it's going to help to talk more about that right now. Okay, so your book talks about center of mass with a rather cryptic way, but hopefully we can understand it by the end of this little talk. It says, the center of mass of a system of particles is the point that moves as though 1, all the system's mass were concentrated, and 2, all external forces were applied there. Okay, it's not super clear, but essentially what they're talking about is F equals ma. So we want to find a point where we add up all the forces in the system and this point accelerates depending on how much total mass we have in our system. Okay, now let's forget about that for a second and just look at what the formula says. It says, how do you find your center of mass? Well, you can find your it's a vector, so it's a position in x, y, z. But you can find your center of mass in the x direction, the y direction, and the z direction separately. So this vector form of the equation is a little bit more complicated. So let's just look at the simplest possible example. Here's our x direction. Okay, and let's say that you have a mass 1 at some position x1. Okay, remember all this is just a line. And you label the points on the line with a ruler or something like that. Now let's say that we have another mass, and this mass I'm trying to draw in an evocative way as to make you think that's a bigger mass. x2. Now let's say that you had this object and you connected them with a massless rod of this sort, and you try to balance them on your finger. Well, if you were going to do that, you know from experience that the place where you balance it on your finger has to be closer to the big mass than to the small mass. And that point is the center of mass. Okay, so that there is some kind of intuitive notion of what this is. Now, to put it another way, let's just see, how would you calculate that number? Well, the m in this formula is the total mass. So in our case, this would be m1 plus m2. And then this is saying add up all of the masses times the positions of those objects. So in this case, my x center of mass equals 1 over the big M. So 1 over m1 plus m2 times m1 times x1 plus, that's what this symbol means, it's a sum, m2 x2. And if you add a third mass on there, you'd add an m3 down there plus m3 x3, etc. Now, as it turns out, this formula looks like it might be bad because, you know, do I need to be real careful about how I choose my coordinates? But it turns out this formula is set up so that it doesn't matter where you choose your coordinates, and it'll give you the right type of spot regardless. So let's look at a more specific example in a couple slides, but just to say it again, why are we doing this? Well, so far in this course, we've just been describing objects that are where the mass can be considered as just a single point. So in this one, we've been just tracking like the middle of a ball. And we haven't been thinking about the ball as spinning or anything like that. But when you have a real object, like even my little pen that I'm drawing this stuff with, I spin it up, it has some of its kinetic energy tied up in the spinning of the pen. It's doing all sorts of weird stuff. However, what we want to be able to do is to separate out some sort of a simple motion within that complicated motion. And the way that we're going to do that is with this idea of a center of mass. So, for instance, if you have a baseball bat, the mass is unequally distributed along that whole thing because the end is bigger than the handle. And so the center of mass is not going to be right in the middle of the bat. It's going to be towards the edge. And so if you flip a bat up, you can see, it's spiraling around. But there should be a point on here that is following our normal 2D projectile motion of a parabola. Okay, so that's the key idea, is that the center of mass is going to be a place that continues to follow the sort of simple motion that we've already studied. All right, so here's an example from your book. If you have a couple masses, they form an equilateral triangle, and it asks, find where is the center of mass of this system. Well, if all of these masses were equal, this would be pretty easy to do. You just draw a bisector on each one of these, and there you go. However, that is not the case we have here. Why? Because the masses are not equal. So the mass 3, this is the most important mass in the system. That's where most of your mass is concentrated. So, all right. Let's go ahead and just try to apply our formula. We've got 3 masses. Our big M, our total mass, is going to be 1.2 plus 2.5 plus 3.4, and that would be in kilograms. Okay. And if we set up our coordinate system the way they do, like this, we can see that this side is going to be, each side of this equilateral triangle is 140 centimeters. Okay, so because we know what our equilateral triangle, this is going to be 60 degrees, this is 30 degrees, this is going to look like our 1, 2, square root of 3 triangle, where this one is our 60 degrees. Okay, so this is going to be 70 centimeters, and this would be 70 square root of 3 centimeters. All right, so now if I want to find what the center of mass of the system is, well, notice what units this has. It has position equals 1 over mass times position. So center of mass, notice it is actually just a position vector. So it's picking out a point in space. So we've taken the kilograms divided by kilograms. In this case, we're going to have a x center of mass. And it's pretty clear that it's got to be between 1 and 140. And how am I going to get that number? Well, sorry, I'm going to take 1 over my big M. This is just a number. This plus this plus this. Times, and here I'm going to have my M1 is at 0.0. So I'm going to have my mass 1.2 kilograms times 0, plus my second point is going to be 70 centimeters on. So this is my mass 1 is 1.2 kilograms. This mass 2, sorry, this is mass 3 right there, is 3.4 kilograms. And my mass 2, as we have it on this picture, is 2.5 kilograms. Okay, so I would take 1.2 times 0 plus 3.4 times 70. Okay, this I'm going to get my center of mass in centimeters. And then I would have plus 2.5, this would be in kilograms, 2.5 kilograms times 140. Okay, so I am going to add these up and divide by the mass, and that'll give me my center of mass in centimeters. On the other hand, for my y center of mass, they've chosen the unit, the coordinates pretty well here, because this is just going to be 1 over m times 1.2 times 0, because the position in the y direction is 0, plus 2.5 times 0, that's this point, plus 3.4 times 70 root 3. Okay, and these are in kilograms. You'd have to divide this by the total mass in kilograms, and then you'd find the center of mass. So I would expect to find it somewhere in this, somewhere up here, and I'll let you look at that example in your book or stick in the numbers for yourself. Okay, so I gave you a homework problem that's pretty similar to this. It's not too much different. Let me just draw it out. You can get set up a little bit. It says a 2 kilogram particle has the xy coordinates minus 1.20 meters. So there's my x. And 0.5. This is meters. So there's my object right there, and it has 2 kilograms. Okay, and we have a 4 kilogram object with at 0.6 meters, 0.6 meters, and minus 0.75 minus 0.75 meters. Okay, so there's our second object. And that has 4 kilograms. Now we're going to put a third object in here. I don't know where it's going to be, so I'll just label it as at xy. Don't know. and it has a mass of 3 kilograms. And it says, where would you put it if you wanted to have the center of mass of that 3-particle system with these coordinates? Okay, well, in this problem, your big M, your total mass is going to be 3 plus 4 plus 2. Okay, so 3 plus 2 is 5, plus 4 is 9. Okay, and if you want to set up your center of mass equations, so you'd have, for instance, your x center of mass equals 1 over m times x1 m1 plus x2 m2 plus x3 m3. But notice how I've already got most of these things because I have my r center of mass. They give me as minus 0.5 meters minus 0.7 meters. Okay, so let's look. I have, this is just part A where they ask what, find this last one. So if I call that x3, y3, for instance. Here I know my x center of mass is supposed to be minus 0.5 meters. I know my overall mass is 2 plus 3 plus 4 is 9 kilograms. I know my x, let's call this m1, m2. My x1 would be minus 1.2 meters. My m1 would be 2 kilograms. My x2, that's this object, would have 0.6 meters as the x coordinate, and then the mass would be 4 kilograms. And then my x3, that's what I don't know, but I am given that my m3 is 3 kilograms. Okay, so this problem is actually not that bad because you know everything in this equation, you just have one unknown. So you don't have to do anything tricky, just plug in all your numbers and then solve for x3. All right, and you can do the same thing with y. So all of this center of mass stuff so far has just been notation and definitions. Now let's do a little bit with it. Okay, and I should just make the point, if we have a system that has a sort of a continuous mass, you know, you could have a funny shape, you could have an object like Play-Doh where you squish down the Play-Doh in one area and have, you know, sort of loopy, fluffy Play-Doh in another. You know, you could have a more complicated setup, but essentially if you wanted to understand the center of mass idea, you could just cut it up in really, really tiny little pieces and call those DMs, and then just use your same definition for the center of mass. So nothing changes conceptually going over to the continuous idea, but you know, you could. It's always the case in physics that you can make an arbitrarily hard math problem. So I don't want to go too far down this route right now because I don't think it's that useful. So let's just bracket this case off. We'll do systems like this when we need to spin hoops and stuff, but let's not do it right now. All right, now, as I've said, the whole point of this center of mass idea is that you're effectively doing Newton's law, but for a group of particles. All right, so we're going to start out with the definition, and I want to prove that I can get an F equals ma out of this thing. So how does this work? Well, my position of a center of mass is defined as 1 over m, remember that's just the sum of all the masses in my system, times m1 r1 plus m2 r2 plus, and I get one of these for each one, mn rn. Okay, so imagine that I have n particles, you get one term in here for each one. Okay, now I can multiply both sides by the total mass, and that gives me something that looks like this. All right? Now, let's do a trick. Let's take the derivative of each side of this with respect to time. So d dt of this, d dt of that. What's the derivative with respect to time of a position vector? Well, he answered, it is the velocity vector. So this is going to be mass times the velocity of the center of mass. So that's how that little point that is your center of mass is moving around. And it's going to equal, I'm taking the derivative of each one of these terms individually now. And if we consider that the mass of these points is not changing, then taking the time derivative of each one of these is just going to make this a v1, v2, v3, all the way up to vn. So it's saying that this is going to give me the velocity of that original vector. So m1, v1, m1, v1, plus m2, v2. These are vectors plus dot, 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 plus mn, vn. Okay, now do it again. All right, so we don't need to belabor this, but the derivative of velocity then is acceleration. So m times a of the center of mass equals m1 a1 plus m2 a2 plus dot, 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 mn an. Okay, and you might say, okay, you're getting a little tedious here, Cordall. Cut to the chase. What's the point? Well, remember, F equals ma. So if this is the total net force on the first object, this is F1. This is the net force on the second object, F2, all the way up. This is the net force on the last object, Fn. So if we define F net as the total force on the first particle plus the total force on the second particle, total force on the all of each particle, this is just the sum of all of those forces, and that's where I get my m a center of mass equals F net. Okay, so now we understand what we mean by this and the point of it. We have now a point that responds to the net force, where that net force is now the sum of all the forces on each particle in our system, and we have a point that accelerates, and it depends on how much total mass we have in our system. Okay, so that's why we define the center of mass the way we did. Now I'm going to give you an example that these are a little bit better examples. For instance, if you have a projectile here that's like a firework, and it's going on a trajectory like this, let's say that you have forces between the different parts. So for instance, you might have a gunpowder blast that causes the different parts of your firework to push off against each other. Now, it might seem to you like, your picture of this thing as a projectile has been completely busted, but the idea of center of mass allows you to continue to think about all of these shards as part of the same system, and these shards, if you add up, their collective motion, they still are going to be following this path. Rather, their center of mass is still going to be following this path. Another example that's given in your book is that of a ballerina doing a jeté. Don't know. I just read the book. I don't really know anything about dance. But the point that they make is that as this ballerina jumps, her path is following a parabola as any other projectile would. But she is clever enough that she knows how to sort of stretch up and down so as to keep her head at a level you know, in a line as she performs this jump. So you can do some clever things with this. Let's give a quick example. This is a problem that I didn't ask you to do for homework because it's a little bit tricky, but I want you to be able to at least understand it. Let's say that it says a stone is dropped at time t equals 0. A second stone with the mass of the first is dropped at the same point at t equals 100 milliseconds. Okay, so the story here is that I'm going to have this first stone having dropped a ways, and it's going to have a V1 and it's got a mass 1. And this is at time equals 100 milliseconds. Now at that time you drop another stone, and this is going to have 2 times mass 1. And then the question asks, what about at t equals 300 milliseconds? Well, just thinking about the physics of this story, what's going to happen at that point is basically that your block up here is going to have dropped down there, and now this second block is going to be going even faster. So the second block, that's the second stone that's dropped, is never going to catch up to the first one. But the thing that they want us to do, so here's your mass of 2m1, here's your mass of m1. It's going to have some speed before, speed after. What you can imagine is finding the center of mass between the two of these. And then you can start talking about how the center of mass is moving. So finding the R of the center of mass, well, you could use your kinematic equations, figure out how far this is moving, and find what that center of mass is by calculating this. And then once you go to the next level, you could go ahead and you could also say that V of your center of mass is equal to 1 over m, so that would be 1 over 3m, 1, times, let's just for clarity call this m2. It would be m1 v1 plus m2 v2. And the thing that would be helpful about this is that it has some initial velocity, which just depends on these two. And if you want to ask how far below the release point is the center of mass of the two stones at t equals 300 seconds, essentially, once you know what that mass is, or that initial speed is of the center of mass, once you know what the initial position is of the center of mass, which you can just calculate that, then you can use F net equals all of these m's times the A of the center of mass. Now, why is that helpful? Well, here, F net is going to be the total force of all of the gravity on these three objects. And the A center of mass is going to depend on the mass of all of these. So if we say, 3mg, where am I getting the 3? It's because you have two masses plus one mass. So 3 times m1 times g equals 3m1. That's the total mass times A of the center of mass. Notice that these cancel out. The center of mass now just drops at G. So the center of mass now acts like its own projectile. It acts just like a dropping ball. Instead of having to consider these two dropping balls, you can just think of this as one dropping ball between the two. Okay, I don't think I'm going to go further in this problem because I tried it in class and it was very confusing. But we'll do more examples of this next time. So be appraised that I know this problem's a little confusing, but the idea is you start out with two objects, you find the center of mass, you find the speed of the center of mass by having a weighted average of the speed of the objects, and then this point is now dropping just like a regular projectile. Okay, let's leave that behind for a second. I want to introduce one more piece of notation in this lecture, and that's the idea of momentum and impulse. Now, momentum, we use the letter P for, and Newton invented this, and I think it was because he wanted to think of the progress of an object, so he uses P. So P is the mass times the velocity of the object. So this is just a vector because the mass is a scalar, v is a vector. It's pointing in the same direction as the speed of an object. Now, why is that useful? Well, if I write m times v, I can always go ahead and rewrite my Newton's second law in terms of this. Why I'm going to do that, I'll show you in a second. Okay, so F equals ma. Okay, that's our F net. F net equals d dt of mv. Okay, acceleration is the time derivative of the velocity. So I can also just write this F net as dp dt. Okay, so it's not too profound. I just wrote momentum, which is m times v, in a different way, and this is it's saying the same thing as Newton's second law. The thing that's a little bit good about this is that if we add up the m times v of all of our particles, it turns out that we're going to be able to have this F net equals the m times a of all of your, or the m times v, how that's changing for all of your particles. So I'm going to talk about that more on Wednesday, but let's just have in the back of our mind that we're going to use this for something. For now, though, let's just see how we're going to use it. And as I said before, just like we had the idea that adding in work changes your kinetic energy, we want to have the idea that adding in something called impulse changes your momentum. So the quantity that we're calling the impulse has units of newtons times seconds. And it's because what the impulse is just the force that I'm applying times the time that I'm applying it. And it doesn't really matter if this is a constant force or not. I can apply more force and then less force. Overall, this is sort of averaging out to some average force. I can always write F average over some time is the integral times of f of t dt divided by the total time, t1, t2. And so all I've done here is sort of put in my F average, and then, it's not really more informative. It's just shuffling around your definitions. But we're usually just going to be thinking about this in terms of average forces. Okay, now, why is that useful? So remember, J is force times time. P, momentum, is mass times velocity. Now, we already said dp dt equals F net. That was a different way of writing Newton's second law. And so I'm going to do the sloppy physicist thing of multiplying both sides by dt. I don't think the math people will let us do that, but they can't stop us. And then we take the integral. So we integrate it from time 1 to time 2. assuming that P is a function of T, do the same thing here, T1 to T2. And notice what this is. This is just your F average times delta T. So on this side, I have my J, that's my average force times the amount of time that I'm applying it. And then over here, I have my P final minus P initial. Okay, so this is how much my momentum has changed. Depends on how much force I apply for how much time. And so, you know, your typical idea of applying a momentum or an impulse is your baseball is coming this way. You apply a quick average force for a quick amount of time, and it totally changes the trajectory of the ball. So you applied a quick impulse, changed the momentum dramatically. And let's just do one quick example with this, and we'll have to come back to this because I know I've introduced a little bit too much nomenclature in one lesson. But let's just read this. It says, in February 1955, a paratrooper fell 370 meters from an airplane without being able to open his chute, but happened to land in snow, suffering only minor injuries. Okay, now this piece is fluff. You don't actually need that. What you need to know is to assume that his speed of impact was 56 meters per second. Okay, so when he hits the snow, he's got some V initial of 56 meters per second. Whoops, not second squared, just meters per second. So that's how fast he's going. We assume that he's reached his terminal velocity. He can't go faster than that because the force of drag pulling up on him is the same as the force of gravity pulling down on him. Okay, and his mass was 85 kilograms. 85 kilograms. And that the magnitude of the force on him from the snow was a survivable limit of 1.2 times 10 to the 5th newtons. Okay, so he's falling down, and the force pushing back on him, trying to stop him, is going to be big. Okay, it asks, what are the minimum depth of snow that would have stopped him safely and the magnitude of the impulse on him from the snow? Now, this looks like a problem that I could really, sort of the best way that I could do it is with my old kinetic energy types of methods. I know how to do this from our last lesson, right? This is going to be doing negative work on him because it's pushing opposite the direction that he's going. So I would go 1/2 mv final squared plus, the final kinetic energy equals 1/2 mv initial squared, and then minus the force times the distance. So it's negative work because it's slowing him down. His final speed is going to be 0. And so once you know that initial speed, I do. You know his mass, I do. You know the force, I do. You can find out what sort of a distance you need to apply that force over. Okay? So part A just asks you what's the minimum depth of snow that would have stopped him safely. So you know the force. They ask you to find the distance. So this is 0. You know all that stuff. You know the force. You can find the distance. Okay, and then part B asks, what's the magnitude of the impulse on him from the snow? Now, the impulse is a force times the time. So there's sort of interesting connection that this makes is that we've connected distance and forces, and now we're putting in extra time. But all you need to know here is that force times time is the same as your delta P. So the impulse is going to be pushing this way, you're going to, it's just like the force slowing him down. Just like there's a negative work on him, there's also be a negative impulse, if you want to think of it that way. And it's going to be your P final minus your P initial. So your final speed is 0, so that is 0. And this is just going to be minus m times v initial. So that gives you your impulse from your change in momentum. Okay, so that's the idea. Just the same way that work changes kinetic energy, impulse changes momentum. All right, so I know I put a lot of new notation on the table today. I apologize for that. Next time we'll be doing a lot more practice rather than just giving new terms. But what are our big points here? Center of mass captures a system of particles as a single point that seems to be acting as a single mass. And then what else did we do? We rewrote our Newton's second law in terms of momentum. Momentum is mass times the speed, or mass times the velocity rather, and the net force is changing that velocity. It's changing that mass times velocity, it's changing the momentum. And then we define the impulse applied to a particle in terms of the net force times, the average force times the time that it's applied. And applying an impulse to a particle will change its momentum. Okay, so I apologize. I know a lot of new notation, a lot of new terms today, not a lot of payoff, but trust me, it's coming. We'll be able to do new problems with this sort of stuff. So thank you for watching, and I'll see you on Wednesday.